in this tutorial we're looking at section 7.4 on implicit and parametric differentiation. Okay, so often we have an equation that is not a function, so e.g. circle. So remember our function has to pass our vertical line test. Okay, in these cases it's difficult, if not impossible, to isolate y by itself. So remember, usually we're trying to find, say, dy dx, where we have y equals some function. Okay, well often we can't actually rearrange to get y as the subject of the equation. Okay, or it might be very difficult. Okay, this doesn't mean we can't differentiate the function, however. So we need to differentiate both parts of the equation separately. Okay, and we need to use the result. Now this is d of y to the power n on dx equals ny to the power n minus 1 dy dx. So basically we differentiate in terms of y and multiply the result by dy dx. Okay, and that sounds a bit weird, but once we start getting into some more worked examples, it will make a bit more sense. Okay, and we also need to remember that dy dx is equal to 1 over dx dy. That comes into a little bit later on when we're looking at our parametric differentiation. Okay, so we'll start cracking into the worked examples. Okay, so this is worked example 13. Okay, so basically we say, given that x squared plus y squared equals 16, find an expression for dy dx in terms of both x and y. Okay, so we've got our equation, x squared plus y squared equals 16. Okay, and we need to take the derivative of each term. So what we do is we say, well, we've got d on dx of x squared plus d on dx of y, so y squared, okay, equals d on dx of 16. Okay, so what that means is, for this, our derivative of x squared with respect to x is our 2x. Okay, and what we do with this one is we take the derivative in terms of y, so that will be 2y, but then we multiply the result by dy dx. Okay, and the derivative of 16, okay, is 0. Okay, so we're getting there. Okay, and now basically we're just going to rearrange our equation and say, well, 2x equals minus 2y dy dx. Okay, and then we can divide by our negative 2y and say that we've got 2x on 2y. So our negative 2y equals our dy dx. Okay, so our dy dx is equal to minus x on y. Okay, so you can see it's a little bit of an odd process, but because we took the derivative of this term with respect to y and multiplied it by our dy dx, remember that's what we're trying to find here. Okay, a derivative of y with respect to x. Okay, so once we rearrange it to make this the subject, then we get our answer. Okay, now, well, what you could have done with this one is you could have actually rearranged and made y the subject for this equation. Okay, it's possible, we can do it. Okay, so we just need to make sure, though, that this can be a bit tricky to do, though, rearranging it. This process means that we're fine no matter what. Okay, so we'll keep moving on. That was our first worked example. Okay. When we have a look at worked example 14, it's got two parts, and the first one is we're going to find d dx of 3xy. Okay, so what we do is we actually are going to use the product rule. So when we're looking at d dx of 3xy, okay, we can think of that as d dx of 3x times y, so spreading it out, okay, which, using our u and v notation, is equal to d dx of u times our v, okay, or if you like, f of x and g of x, if you've heard to use that notation. So what we do is we say, well, let u equal 3x and let v equal y. Okay, then our du dx, that's going to equal 3. Okay, and our dv dx, okay, is really going to be our derivative of this one with respect to y, which is 1, times our dy dx, okay, or just dy dx. Okay, so that means then our d dx of u dot v, okay, is going to be, going by our chain rule, remember it's u times dv dx plus v times du dx. Okay, well, we know our u is 3x. Okay, we know our dv dx is really our dy dx. Okay, plus our 3, or our y, sorry, times our 3, which makes us 3y. Okay, and so that's what we can say our d dx of our 3xy is equal to. Okay, because remember we made our dx, d dx of 3xy equal to our d dx of u dot v, okay, by expanding it out here. Okay, so that is actually our solution. Okay, so that certainly looks a bit different, okay, but that is actually our solution. So our solutions are looking quite different to what we're used to. Okay, the second part is find dy dx for 4x cubed plus 3xy take 2y squared plus 5x take 7y plus 8. Okay, so what we do is we take the derivative of each bit separately. So we say dy dx of our 4x cubed, okay, plus our, oh sorry, that should be dy, should just be our d, so d dx of our 3xy plus d dx of our minus 2y squared. Okay, or sorry, yeah, we can go like that, or sorry, what they do in the book is they take the negative out and say it's take, okay, and then plus d dx of 5x take d dx of 7y, okay, plus d dx of 8. Okay, so there's a fair bit to that, and that's all equal to our 0 still. 0 equals up that way, if you do. Okay, so we go through and we do the parts that we can do. Okay, so we know our 4x cubed. Okay, well that's going to become our, sorry, that should be 4x squared, not cubed, squared, sorry. Okay, that's going to become our 8x. Okay, this one here, okay, that's going to become our 3x. Okay, so we're going to take the derivative with respect to y, okay, which leaves us with our 3x times our dy dx. Okay, then we're going to take away then we've got in here, sorry, give me 2 seconds. Oh, sorry, I've just realised what we need to do there. Sorry, I was just not realising what the step was. So, what we're doing is for our d of 3xy dx, sorry, we've got to use our result from here. Okay, from part A. Sorry, I hadn't spotted the link between those two. Okay, so we use our result from here to find our derivative of this part. Okay, now for here we've got to take away, okay, our 4y dy dx, okay, because remember we're taking the derivative in respect to y and times it by our dy dx. Okay, next one will be plus 5. Okay, our next one will be, that should be take 7y, so it'll be take 7 dy dx. Okay, because it was a y term. Okay, and the last one just cancels out. Oh, we know all of that equals to 0. So what we can do is we can start rearranging some things. So what we want to do is get all our dy dx's on one side. Okay, so when we do that, we can say that we get 8x plus 3y plus 5 equals 7 times our dy dx, right, plus 4y times dy dx, okay, take 3x dy dx. Okay, we can take our dy dx as a common factor, so we say our 8x plus 3y plus 5 is equal to our dy dx, outside of 7 plus 4y, take 3x, okay, and we can simply divide by this term, okay, to get our dy dx by itself. So say our dy dx is equal to our 8x plus 3y plus 5 over 7 plus 4y, take 3x. Okay, so it's only this term here that was a bit tricky, okay, which is where we've done our product rule previously in the first part. Sorry about that again, I didn't pick that up straight away. Okay, so we'll keep moving on. We've got 2 more worked examples to go. Okay, we've got given that e to the power of 2xy plus 3 sine of 2x take 3y equals c, where c is a constant. Find an expression for dy dx in terms of both x and y. Okay, so we've got our equation, e to the negative 2xy plus 3 sine of 2x take 3y equals 0. Okay, so we're just going to start off with do our d dx of our e to the negative 2xy plus d dx of our 3 sine of 2x take 3y. Okay, and sorry, it doesn't equal 0, that equals c, which means we go our d of dx of c. Okay, so we just consider the first term to start off with. Okay, and we need to use implicit differentiation. Okay, so what we're going to do is we're going to just look at this part first. I might change the colours. Right, and what we're going to do is say, well, let our u equal 2xy. Right, that means then that we're trying to find d dx of e to the negative u. Okay, for that one. Okay, and then because we're doing that, we really need to make it then that we're finding our derivative with respect to u, which is of e to the negative u. Okay, and we're going to have to times that by du dx. Okay, so using the product rule, okay, then what we do is we find, well, the derivative of this part is going to be our negative e to the negative u, okay, d dx, okay, of our 2xy, because it's our du dx. Okay, so when we do that, okay, we'd have to use the product rule on this part as well. Okay, which means we've got negative e to the negative u, okay, times our, okay, if we're doing the product rule here, okay, now there's skipped a fair few steps in here, we're doing the product rule, okay, but you need to do a 2x and a y, like we did in the times y, like we did in the previous one, and when we do that, we get our 2y plus 2x dy dx. Okay, so that's using the product rule on this part, okay, just like we did in the previous worked example. Okay, so then we can say, okay, we can sub in our u back in, okay, and say that our d dx of e to the negative 2xy, okay, is equal to our negative e to the negative 2xy by subbing u back in that we had here, outside of our 2y plus our 2x dy dx. Okay, so we're going to leave that term alone for a while. Right, we're going to have a look at the second term, which I'll do in the black. Okay, so this time we're going to say, well, we're doing just this part here. Now, what we can do there is let v equal 2x take 3y. Okay, so that means then that we're finding d dv, okay, of 3 sine of v times dv dx. Okay, so our dv dx, okay, is going to equal our 2 minus, so when we look at this bit, okay, we're taking the derivative of v with respect to x. Okay, so we take the derivative of this bit with respect to x. Okay, and then we take the derivative of this bit with respect to y, and then do our times by dy dx. Okay, so we've got to make sure we do that. So that's that part, okay, taken care of, and then we say then that we've got our d of dx, okay, of our 3 sine of 2x take 2y, well, that's equal to our 3 cos of v, okay, by taking the derivative of this part, okay, times by our dv dx, which we know, okay, is our 2 take 3 dy dx. Okay, because we know the derivative of this bit. Okay, we know that bit. Okay, so we'll keep working through. Okay, so we substitute back in our v value, okay, and say our d of dx of our 3 sine 2x take 2y is equal to our 3 cos of our v, which is 2x take 3y, okay, by our 2 take 3 dy dx. Okay, now we can substitute for the first and second terms. Okay, so we've put all this stuff back together now. Okay, so we know that we've got all this part, we've got all this part now. Okay, so what we can do is I might change back to the blue now. So, well, we know this bit is equal to our e to the negative 2xy, so the 2y plus 2x dy dx, okay, plus we've got this part, which is our 3 cos of 2x take 3y outside of our 2 take 3 dy dx. Okay, and we know, okay, derivative of our constant is just equal to 0. Okay, so it doesn't look very good. Okay, we've got to expand our brackets at this point. Okay, right through. So we've got here minus 2y e to the negative 2xy minus 2x dy dx, okay, plus our, sorry, to make sure I haven't missed anything, plus 6 cos of 2x take 3y, okay, minus 9 dy dx, okay, cos of our 2x take 3y equals 0. Okay, there's a bit going on there. Okay, so we can transpose the equation so we get all our dy dx's on one side again, like we did in the previous worked example. So when we do that, we get our negative 2y e to the negative 2xy, okay, plus our 6 cos of 2x take 3y, okay, equaling our 2x e to the negative 2xy dy dx. Oh, sorry, I missed that in this stage here. So when we multiply through that by that and that by that, sorry, this should be 2x e to the negative 2xy, which is what we've got here, dy dx. Sorry about that. plus our 9 cos of our 2x take 3y dy dx. Okay, so what we can do is we can bring out everything here that has, we bring our dy dx out as a common factor from there. Okay, and then what we can do, I'm going to skip that step because I'm going to run out of room. So we can bring this out as a common factor. Okay, bring the outside of all this stuff, and then we can divide by all this stuff left over. Okay, which means our dy dx equals 6 cos of our 2x take 3y minus our 2y e to the negative 2xy. Okay, it's just these around the other way so that we don't have this negative at the front, over our 2x e to the negative 2xy, okay, plus 9 cos of 2x take 3y. Okay, so a fair bit going on. So sorry about this step in here, and that is a mistake in the textbook. Okay, which is where I went wrong. Okay, so just make sure that you remember that this one was actually times by that. Okay, so as you can see, fair bit going on in these worked examples. Okay, we've got one more to go, and then we're done for this section. Okay, so we've got if x equals 3 cos of t and y equals 4 sine of t, find dy dx in terms of t. So this is one of our parametric equations. Okay, so hey, we'll get cracking into this one. So we've got x equals our, right, I'll switch text this down. Got x equals our 3 cos of t. Okay, that means that we can say our dx dt, dx dt equals our minus 3 sine of t. Okay, and we can say we've got our y equals our 4 sine of t. So dt is going to equal 4 cos of t. Sorry. Okay, so we can say then our the chain rule, our dy dx equals dy dt times dt dx. Okay, so that we'd switch these around. Now you see though we don't have dt dx, we've got dx dt. So our dt dx is 1 over this part here. So we can say then that our dy dx is equal to our dy dt, which is 4 cos of t times 1 over minus 3 sine of t. Okay, so that means that we can say our dy dx is equal to 4 cos of t over minus 3 sine of t. Okay, which means we can say that dy dx is equal to negative 4 on 3 cot of t. Okay, because remember cos over sine is 1 on 10, which is cot. Okay. Okay, there is part B, okay, to this one, which we'll have a look at. I just didn't write on because I wasn't sure how much room we'd need for this part. Okay, which is for the parametric equations, x equals 3 cos of t, okay, and y equals our 4 sine of t. Okay, we want to find an implicit relationship between x and y and find the gradient. Hence, verify your answer to part A. Okay, so we're doing a different process to actually work this out, okay, to get to the same answer. Okay, so what we're saying, okay, here's we're going to start off by actually getting cos of t by itself. So we're going to say cos of t is equal to x on 3. We're going to say sine of t is equal to y on 4. Okay, we know cos squared plus sine squared equals 1. So what we can do is we can square both of these. So remember, cos squared plus sine squared equals 1. So we can say then that x squared on 9 plus y squared on 16 equals 1 by squaring both of these terms. Okay. So now we've got to use implicit differentiation. So what we can do is we can say, well, 1 on 9, okay, d dx of our x squared, okay, plus 1 on 16, d dx of y squared equals our d dx, okay, of 1. Okay, well, we know here our derivative of x squared in terms of x is 2x, and we've got to be over 9, so we can say 2x over 9. Now this one we can say is going to be our 2y on 16, dy dx, okay, and that's going to equal 0. Okay, so we can rearrange these, okay, and say then that we've got our 2x on 9, okay, equals minus y on 8 dy dx, just simplifying our 2 over our 16 and bringing that side across. Okay, we can then say then that our dy dx, okay, if we divide by our negative y on 8, will give us negative 16x on 9y. Okay, but we know what x and y equal. We've got them up here, so we can sub those back in. So dy dx equals negative 16 times 3 cos of t, okay, over 9 times 4 sine of t. Okay, which we can cancel out some 3's and things like that, and cancel out some 4's. So we get our dy dx is equal to our negative 4 on 3 cos of t on sine of t, okay, which, as we found a minute ago, is the same as our minus 4 on 3 cot of t. Okay, so there's just a bit of a different way that we could go there. Okay, so this one we use our chain rule, okay, and differentiate each bit separately. Okay, to get an answer, this one we came up with our relationship first, okay, and then found our derivative. Okay, so these look quite different to differentiation that we've done in the past, and certainly a lot different to the differentiation you're going to have been seeing in maths methods, but hopefully it's enough to get you through. I know it is quite challenging in this section, but hopefully you can get through all the questions.